It is time for the second talk of our conference. The second speaker is Professor Chihiro from the University of Tokyo, and she will talk about quantum thermalization and solvability.
Thank you. So, okay, first of all, I'd like to thank the organizers for giving me an opportunity to give a talk at this very interesting workshop. So today I'd like to talk about quantum thermalization and solvability. So this talk is based on 3 papers, one of which is already published, and the second one is recently put on arXiv, and the last one is still work in progress, but I hope we'll complete this paper very soon. So let me first introduce my collaborators. So this talk is based on the collaboration work with Hoshio Katsura from the same university, but he's in physics department. And Chiara Paletta and Balázs Porsogay. These 2 people are mathematical physicists. And actually, I myself is also mathematical physicist. So my research area is quantum integrable systems from a statistical mechanics viewpoint. So, okay, so this is the outline of my talk. And I think the topic of this workshop is very diverse. And I guess most of the audiences are mathematicians. So is there somebody who counts oneself as a physicist? Maybe no. Okay, so, and I'm sorry for using this PowerPoint, because I know that the mathematicians prefer Blackboard talks, but I wanted to show some figures. I'm not really good at drawing the things, so please forgive me to using PowerPoint. And I also know that the mathematical physics for mathematicians is not like mathematical physics, but more like physics flavor mathematics for physicists, actually. So as you can get from what I'm saying, I count myself as a physicist because the motivation of my research always comes from the physics. But don't be scared, so I try to explain the very basics of the motivation of my research. Okay. So I think the dream of most theoretical physicists is to find a series which describes our world in a unified way. So the string theory is one of those attempts which tries to describe our universe in a unified way. But actually, there is a smaller universe in a microscopic world. So actually, physicists know that there exists a common series which describes both microscopic world and the macroscopic world. And so one of those examples is actually quantum integrable systems. So the aim of this talk is to connect the microscopic world and macroscopic world by using this quantum integrability or some kind of solvability. We of course know that the unified theory is still under construction, but even the phenomena which can be observed, widely observed in our real life, is not understood. It's not very well understood yet. One of the typical examples is the thermalization. So have you ever heard of thermalization? Thermalization is a macroscopic physical phenomenon which can be widely observed in our real life. And almost all physics systems are supposed to reach the thermal equilibrium state, and we call this phenomenon the thermalization. For instance, if we have a hot coffee and leave it for a long time, then the temperature of coffee becomes like the coffee gets cold after the long time, and then the temperature reaches the temperature of the room temperature, right? And another example can be observed in cold ice cream. So if, of course, the cold ice cream is very nice in summer, in hot summer, but if we leave it for a long time, we can easily get cold ice cream completely melted, which is very pity. So these 2 are the typical examples of thermalizations. So the thermalization occurs by the heat exchanging between the object, and the external systems, which you call the environment, until the temperature of the object reaches the temperature of the environment. Once the temperature of the object gets reached at the temperature of the environment, then this temperature never decreases than it, nor raises again. So the thermalization is an irreversible process. Okay, so this is very important. However, surprisingly, the microscopic description of the particle systems are always always describes a reversible process because it has time reversal symmetries in very often times. This I explain later. So before explaining this, I think it would be helpful to give you the properties of the thermal equilibrium state. Now, in the thermal equilibrium, all macroscopic variables must have constant values. Especially if we look at the macroscopic current, this must have a value which is completely zero. If all macroscopic variables have some constant values, but the macroscopic current also has some constant non-zero values, we call this state as the non-equilibrium steady state. So this is the difference between the thermal equilibrium state and non-equilibrium steady state. Okay. And the second property of thermal equilibrium is the equilibrium state must be characterized by a few number of macroscopic variables. So if we have two distinguished equilibrium states, then these two equilibrium states must be distinguished by a finite number of macroscopic variables, even in the thermodynamic limit, which is large volume limit. Of course, in the large volume limit, we have infinitely many degrees of freedom from the microscopic viewpoint. So this is very, very surprising fact. Okay. And the last property I want to show about thermal equilibrium state is almost all microstates are macroscopically undistinguished. So suppose we have many distinguished microstates. So all these microstates are distinguished from the microscopic viewpoint with different microscopic information, which is given by the coordinate or momenta of each particles. But if we measure the macroscopic variables such as energy, particle numbers, okay, it could be some total momentum or pressures, and then all these must have the same values on all different microscopic states except for some exceptional microstate, which can be distinguished from the thermal state in some sense. Okay. So these three are the key properties of the thermal equilibrium state. Okay. Any questions so far? Okay, so now let me move on to the microscopic description of the system. So we know that atoms, molecules, or any kind of particles obey the equation of motions, which is given by Newton's equation of motions in the classical mechanics, or the Schrödinger equations in the quantum mechanics. But surprisingly, both of these equations very often have time reversal symmetries. So the example can be obtained by setting the potential of Hamiltonian to be time independent. Then we can easily say that these equations are time reversal symmetric with respect to time reversal. Okay. So the question is, how can we explain the thermalizations, the macroscopic phenomena, macroscopic irreversible processes from the microscopic viewpoint by using these equations, which describes the time reversible processes. Okay. And moreover, it is not really clear whether the isolated quantum systems can thermalize or not because of the following sort of experiments. Okay. So I want to consider the following setup. So suppose we prepare the initial state as a linear combination of the energy eigenstate with some certain coefficients, which is given by C here. and then evolve this initial state by time according to the quantum mechanics. So I apply some unitarity operators to this initial state, which is usually described by the Hamiltonian energy operator of the system. Then we will get to this expression. So this is again the linear combination of the energy eigenstate, but with different coefficients compared to the initial state, okay? And then we want to measure a certain observable on this quantum state at time t, and then we get this expression. So this represents just the inner product between these states. But here you can see some oscillating time by oscillating terms by time. So this completely contradicts to the fact that the property of the thermal equilibrium, which requires a constant value of some observable, right? So we don't want some oscillations by time because we really need to have constant values by time in equilibrium state. And another thing is, even if we take the time averages of these values, then we get this expression, which strongly depends on the choice of the initial state. So this also conflicts to the property of the thermal equilibrium, which requires to be characterized by only by a few number of macroscopic variables, because this arbitrary choice of initial state contains many informations, many microscopic information, so we don't want this expression. So does this mean the isolated quantum system never summarizes, or is there some way to understand these kind of things in a macroscopic way? So this has been a long-standing problem in statistical mechanics, but very recently there was a big progress about understanding this kind of problem. The first question of oscillating by time has been answered by answered in 2008 by the following statement. Suppose we have an initial state, which is the linear combination of many enough energy eigenstates. Then this initial state can react to some certain kind of diagonal ensemble after a long time. The statement says that the deviation of the expectation value of some observable from the its time average becomes very, very small, much smaller than its operator norms. Its operator norms if the initial state is prepared to be the linear combination of enough many energy eigenstate. So this confirms at least a certain kind of initial state can react to a certain kind of non-equilibrium steady state or equilibrium state. But here we see that, as we already saw in the previous slide, this time averages contains information about the initial state. So this does not say anything about the relaxation state, completely matches to the thermal equilibrium state. So how can we understand these problems? So this is actually the second question, which I showed in the previous slide. And this question has been also answered very recently in 2017. So the statement is almost all energy eigenstates are macroscopically undistinguished from the thermal state. So the key point is that we have to choose this observable to be the macroscopic observables. Here macroscopic means like, okay, so we don't have a complete definition of macroscopic variables actually. So this is still an open problem in statistical mechanics. But in the proof of these two papers, they impose two key properties on the macroscopic variable. The one is the locality. So, okay, it's a summation of local operators. And the second one is the translation invariance. So macroscopic variable should be local operator with translation invariance. So under these two assumptions, they prove that the probability to obtain the energy eigenstate to be different from the thermal state becomes very, very small in the thermodynamic limit. So this diverge, this decreases as the number of energy eigenstates in the energy cell grows. So actually, this W is the exponential of the volume. So this right-hand side is something like E2 minus E2 volume. So this becomes very, very small in the thermodynamic limit, which is the large volume limit, okay? So with these two statements, it seems like most of the initial state related to the thermal equilibrium state. So actually, the second statement is a very, very strong statement, but this statement does not forbid the existence of the exceptional non-thermal energy eigenstate. So actually, it has been reported that there exists the exceptional non-thermal microscopic state in the classical systems from the old time. A typical example can be observed in the movement of the billiard. So this is a billiard ball moving on the oval stadium. So if the billiard ball starts to move from a generic point, then its movement is a trajectory of its movement cover all over the stadium algebraically. But the ball starts to move from near unstable periodic trajectories. Its movement is restricted in a very small region of the oval stadium. So this motivates us to consider that ergodicity is some kind of very important properties for the thermalization to occur. And without these ergodicities, the effect of non-thermal microstate becomes very large, which prevents the system to thermalize, okay? So this is the classical example. And we can apply the similar way of thinking to the quantum system. But in the quantum systems are defined as the vector in the Hilbert space. So we need to consider the ergodicity in the Hilbert space, okay? So we expect that the thermalization of isolated quantum systems does occur as long as their dynamics is ergodic in the Hilbert space. But if there exists some isolated, relatively small invariant subspace, then we cannot say the isolated quantum system can thermalize because it violates ergodicity in the Hilbert space. So here I showed two typical examples of the Hamiltonians which never thermalized. The first one has the Hamiltonian which has relatively small invariant subspace. So if we prepare the initial state in this subspace, then this cannot move out from this subspace W during a time evolution. So this means if there is the exceptional non-thermal energy eigenstate in this subspace, we cannot say the system do thermalize, okay? And the second example is the Hamiltonians with this block diagonal structures. So the number of block diagonal, the number of these blocks exponentially grows as the system grows. So in this Hamiltonians, we never see the thermalization occurs. So this is a little bit different from the first case, because if we prepare the initial state in this large subspace, then we can say that the system do thermalize. But in the second case, we never observe thermalization because it's fragmented into exponentially many subspaces. Actually, the notion of this fragmentation is not really necessarily not necessarily related to the solvability of the Hamiltonians, but sometimes it is possible to embed the solvability into this system. And I think I forgot to mention that this relatively small invariant subspace in the first case usually shows up as the subspace consisting of the solvable states, solvable vector, eigenvectors of the Hamiltonian. And this is because the reason why we observe this completely isolated subspace is there exists extra algebraic symmetry in this subspace, which is true only in this subspace, but it's not true in the entire Hilbert space. Of course, it is not so easy to check whether the state is really non-thermal or thermal unless we compute all of the macroscopic observable. We even don't have the definition of macroscopic observable, so it's almost impossible. But actually, there are some signs which says the state is really non-thermal. The first one is the persistent oscillation. So if we observe the oscillation remains after a long time of the time evolution, then we conclude that this is not the this is not the thermal state, but in the thermal, because in the thermal equilibrium, we need the constant value of macroscopic observable. The second one is relatively small entanglement entropys compared to the ordinary thermal equilibrium state. The thermal equilibrium state gives rise into these thick curves, and this entanglement entropys growth is proportional to the volume of the systems. But if the state is non-thermal, and especially solvable, then its entanglement entropy stays relatively smaller than the ordinary thermal states. So this is another factor. These two have completely different properties, and we conclude that these states are something different from the normal thermal equilibrium state. Oh yeah, I think this is a very physical way of thinking, but anyway, it works so far. Okay. Okay, so these two examples can be observed in the first case of this non-thermal systems. And this is about quantum integrable systems. Actually, the quantum integrable systems are exceptional quantum systems which never thermalize. Okay? So integrable systems, it has been known that the state relaxes to a certain state, but this state is different from the thermal equilibrium. So indeed, we see the emergence of non-zero macroscopic current, although this takes constant value. So we can say that the integrable systems reaches to some relaxes to some non-equilibrium steady state, which is called generalized Gibbs ensemble. So these are the numerical results of the time evolution of some object. The object must be, okay, so particle density profiled with respect to momentum. So this red line, which is noted by GE, is the thermal equilibrium values computed theoretically. And this GGE is the computation based on generalized Gibbs ensemble. So here you can see after a long time, the quantities indeed reach to the generalized Gibbs ensemble, which is different from the thermal state. So this is a non-equilibrium steady state, which include many conservative quantities arises because of the integrability. So in the quantum integrable system, there are many conservative quantities which grows as the system size grows. So if this GGE contains the number of the many conservative quantities which is produced by the integrability, this means that this steady state is characterized by infinitely many conservative quantities in some dynamic limits. So this contradicts to the property of thermal state because it must be calculated only by a finite number of conservative quantities. Okay. So this is the reason why we distinguish a generalized Gibbs ensemble from ordinary normal thermal state. Okay. So this is the motivation part. And then now I want to show some examples of solvable and partially solvable models based on two different mechanisms. Okay, so here I want to use two different notions of solvability. The solvability and partial solvability means we say the model is solvable if all energy eigenstates are analytically derived for some reasons. And we say the model is partially solvable if all the energy eigenstates in a target subspace are analytically derived. But we say the system is integrable if its solvability is based on the Yamaguchi equation. So solvability includes the integrability in this talk. So of course, there are many definitions of integrability and solvability, but I want to use this definition in my talk. The first one is simply about the solvability of the models. So this is not related to the Maxwell equation. Maybe it's possible to put into the framework of the Maxwell equations, but I just want to explain in another way. Okay. So the first mechanism which brings the solvability to the system is the spectrum generating algebra. So the spectrum generating algebra is defined by the existence of the local operator Q, which does not commute with the Hamiltonians. So this is a commutator. So does not commute with the Hamiltonians, but proportional to the local operator itself. This E, as this frag E, is just some real number, which is supposed to be a certain kind of energies. So with these dynamical symmetries, we can construct the energy eigenstate in the following way. Once we find the trivial energy eigenstate, which is often zero energy eigenstate, which I denoted psi 0, and then we can apply the local operator to this state, and then we can subsequently construct the other energy eigenstate. Okay? So in this case, the energy spectrum is equally spaced, whose interval is given by this E. And this is a very simple computation. So where can we observe in this kind of dynamical symmetry in the real systems? So this is a very simple algebra. So we can already observe this kind of algebraic structure in free fermion models. Maybe some of you know the free fermion model because it is very famous quantum field theory model. So in my case, I usually prefer dealing with some discrete system because everything is very simple. Okay, so if we write the Hamiltonian, the energy operators is a momentum space. This is given by just this quadratic terms. Okay. And of course, this eta dagger and eta are the fermion creation and fermion annihilation operators. So they satisfy the anti-commutation relations. So if I write AB here, then this represents AB plus BA, for instance. So this is the fermionic anti-commutation relations. And with these relations, we can easily find the spectrum generating algebra can be observed for the Hamiltonian and this fermion creation operators. If we look at this Hamiltonian, it is easy to observe that the vacuum state, the state without the fermion, it can be the zero energy eigenstate because the square of eta, the square of eta and the square of eta dagger is equal to 0. Okay. And then we can construct the tower of solvable energy eigenstate just by applying the fermion creation operator to this vacuum state. So this is a kind of a generalization of the previously obtained spectrum generating algebra because it contains many of these creation operators. So it's a kind of multi-species models of the spectrum generating algebra, which I showed in the previous slide. And then once we get the energy eigenstate, then we can compute the energy eigenenergies as well. So this is a very simply solved model. And a slightly more complicated example can be observed in different models, but I will skip it. And we saw that this is a completely solvable models, but it is also possible to impose these dynamical symmetries only in a certain subspace, but not in the entire Hilbert space. So the partial dynamical symmetry, which I call the restricted spectrum generating algebra, is defined by the existence of the local operators, which whose commutator with Hamiltonian comes back to the original one only in the subspace of some Hilbert space. Okay. So the story is the same as long as we stay in this subspace. So once we find a solvable energy eigenstate in this subspace, then we can construct the other energy eigenstate just by applying this local operator Q. And then we get the equally spaced spectrum in this subspace. But of course, this is only the story. This is a story only in this subspace. So we cannot solve all the energy eigenstate in the entire Hilbert space. And here you see we have the equally spaced energy spectrum. So if we compute things on this on the initial state prepared in this solvable subspace, then we will get the oscillating terms whose frequency is given by the intervals of the energy spectrum in this solvable subspace. Indeed, if we compute the things in the models with solvable subspace raised by partial dynamical symmetry, then we will see the emergence of persistent oscillations in. Okay, so this is some kind of inner product between the initial state and the vector at the time t. Okay?
So can I get the initial state to the gapped state? Because
Sorry again.
Your initial is the gapped state or gapped?
Okay, so this is gapped in the subspace, but not necessarily in the entire Hilbert space. This is a story only about this subspace. Okay. Okay, so which model can have this restricted spectrum generating algebra? The simplest example can be observed in spin 1 XY model. So the spin 1 XY model is defined by the Hilbert space, which is given by the tensor product of the local three-dimensional complex Hilbert space. Okay? So these are the orthonormal basis of the C3. And local Hamiltonian is given by these tensor product expressions, each of which is given by 3x3 matrices, which we call the spin 1 spin operators. So this is known to be non-integral of spin chains in the sense that there is no Yambax equation behind this model. So of course, we cannot solve all the energy eigenstate analytically, but we can easily find the trivial energy eigenstate, which is given by all up state, all the up state. So we will call this up and down, but the state with all two or all zeros. So this is a certain kind of vacuum state. And then the other state, which is given by the excitation, the excitation state is also solvable. So in this case, the quasi-particles are spin 2 magnons, which carries the momentum pi, because this is expressed as e to I pi x. And the solvable subspace is constructed by applying this creation operator to this. Oh, 2 is okay. So this one. So all the same state at each side. So we can choose, or we can also choose all zero state instead. These are the highest weight or lowest weight of U, maybe SL2 in this case. Okay. I said two with two three-dimensional representations. So as long as we choose this all the local state to be the lowest state or highest state of SA2 of three-dimensional representations, then this state becomes the energy eigenstate. Okay? And then the other solvable energy eigenstate can be constructed by applying these quasi-particle creation operators. And the reason why these states are solvable is understood by restricted degenerating algebra, because this quasi-particle creation operator satisfies the restricted spectrum of generating algebra with the Hamiltonian in this solvable subspace. So this is a very simple story because it is easy to find this state is energy eigenstate. And of course, the most difficult process is to find the solvable energy eigenstate. A single solvable energy eigenstate in a solvable space. Okay? And a slightly more complicated example can be observed in AKLT model. This is like an Affleck-Kennedy-Lieb-Tasaki model. I think this is also famous model in discussing the topological nature of the spin chains, which some of you are familiar to. But today I don't want to talk about the topological nature of these models. And the Hamiltonian is again given by this non-integrable spin one chain. So it's a tensor product of the local three-dimensional complex Hilbert space. Okay, and the local Hamiltonian is given by complicated expressions, but if we choose the parameters in a proper way, we can recover the original AKLT model, which is just given by the projection onto the spin 2 state. Okay, so maybe you are not you are mathematicians, so you are not really interested in this kind of stuff. We can just look at these expressions. And the point is that this model is not integrable, but the ground state and some excitation state has been known to be solvable from the old time, but people didn't know why. And very recently, it has been found that the solvability of these states can be also understood by the restricted spectrum generating algebra. So it has been known that the energy eigenstate, which is the ground state in very often times, it's given by the matrix product state. So this is a very complicated expression. So this, okay, so let me start by explaining K here. So K is just identity operators for periodic boundaries, and K is some rank 1 matrix if we impose the open boundaries. So K is determined by the choice of the boundary conditions, but here I often use the periodic boundary conditions. So you can just put an identity operator here. And A is some matrices, which is given by this one. So if we combine, so this is, okay, so you can say that each of the subscript M1, M2, and Mn runs over 1, 0, 1, 2. So it can be written as the vector with 3 components, but each of the element is given by the matrices. Okay, so sigma plus, sigma d, sigma minus as a Pauli matrices. So these Pauli matrices are 2 by 2 matrices. And okay, so this is actually the explanation for the physicists. You don't need to care about this. It's just mentioning the dimension of the auxiliary space, which never shows up in the physical systems. So this matrices acts on the auxiliary space, which is not a physical space. So we need to kill this degree of freedom by taking the trace. Okay.
Can I ask you about this one? About the ergodicity?
Ergodicity. So
is there still weak? You can apply a failure?
Yes. So this model belongs to the first type of this non-summarizing condition.
That's your model, not your model of AKLT.
AKLT belongs to this one.
Right.
And this I'm going to construct this solvable subspace. So I'm not going to talk about this one.
So still you have the spin one case we can apply on anything.
Yes, but it is not obvious that there exists a matrix product state with a small bond dimension for the energy eigenstate. Okay, so this is the exact expression, analytical expression of the exact energy eigenstate. And for the excitation state, we can also apply the same things just by applying a quasi-particle operator again. So here I replace the vector A with the vector B at the position of quasi-particles. So the V and the vector V is just given by applying this plus square operator to the vector A. Okay. So, okay. So this actually provides exactly solvable energy eigenstate of the KLT model, and the reason is understood in the following way. Yes, sigma plus, sigma d, sigma minus, 2 by 2 matrices. Okay, so this vectors lives in another spaces. Okay, so if we have m equal to 0, then it acts on this is possible. It's like 1, 0, the vector 1, 0, 0. So if we apply the vector A to the state 0, and then we get A0 sigma plus. Okay, so if you regard these elements as just as scalars, then these vectors acts on this space. But they have an extra degree of freedom, which is included in the inside of the elements of these vectors. So if we apply the vector A to this vectors, then there are certain degree of freedom about this choice of Pauli matrices remains like this. Okay, so maybe it is weird. Okay, so I cannot find his chokes. Okay, so maybe I will explain you later more. Okay, so why can we express the energy eigenstate in this matrix product way? So this is the matrix product state for the energy eigenstate, and if we apply the local Hamiltonian, this the tensor product of the vector A, then we get the local divergence conditions or persuasion-free conditions. So in order to get this one, we can make a summation over all the sides, which provides just the axiom of the Hamiltonian on the product of the tensor product of the vector A. But in the right-hand side, we get simply 0 because of the trace because of the periodic boundary conditions, which means this matrix product state provides the energy eigenstate of the Hamiltonian. Okay. So for the excitation state, we impose one more algebraic relation, which I call the local eigenvalue conditions, which is given by this expression. And then we can simply observe that the single excitation state, it's given by the simple excitation provides the exact analytical energy eigenstate of the Hamiltonian. And together with these irreducible properties of quasi-particle state, we can even construct the merge quasi-particle excitation state as the exact energy eigenstate of the AKLT Hamiltonian. Okay, so this is just the complicated computations, but the derivation is not so difficult. Okay, so I only gave the local conditions, so local divergence conditions and local eigenvalue conditions, but all together it turned out that these local conditions are the sufficient conditions for the Hamiltonian to satisfy the restricted spatial generating algebra with the quasi-particle Fuchsian operators in the solvable subspace. So it's a very technical problem, so I'm sorry for this. But in this way, we can produce a kind of partial solvability for the AKLT model. And we can apply the same method to any other models in the same way. So these are the series of the partial solvability due to the restricted spectrum generating algebra. So what's annoying is that these quasi-particles are all identical and non-interacting quasi-particles. So we want to extend this method to the interacting quasi-particles, and it is sometimes possible although we lost some of the recursive properties, so we need some technical data, more technical data, but somehow it seems to be possible for a certain kind of models. So I don't have enough time, so I will skip this one. But, okay, so now I think it's better to proceed to the integrability. So there is no clear definition about the quantum integrabilities. So it is often said that the system is integrable if there exists a mathematical structure called Yang-Max equations. So Yang-Max equations guarantees a many-body scattering, the decomposition of the many-body scatterings into a sequence of two-body scatterings, and the observer's result, the physical property, does not depend on the way of the decomposition of, okay? And then, by using these Yang-Max equations, we can construct the commuting transform matrices, which is defined by the product of the solution of the Yang-Max equations in this way. And then by expanding the transfer matrix with respect to the free parameter lambda, this is just complex numbers, and then we can get infinitely many commuting conservative quantities, which is local in very often times. So in this way, we can compute any kind of correlation functions, and we can point out the relation to the quantum groups. And there is some connection also to the conformal Phys series, and many of mathematical styles appears in relation with these algebraic structures, which is very nice. And we can also embed the integrable models in some part of the fragmented Hamiltonians. Okay, so. Okay, so I don't have enough time, so I will simply give some idea of these embeddings. So the simplest example is observed in this Hamiltonian. So this is non-integrable Hamiltonian, but if we carefully look at the interactions, we can see that this Hamiltonian only exchanges the neighboring configurations. So this means a Hilbert space is fragmented according to the multi-set of the configuration entries. So number of each entries never changes. They just exchanging each positions by applying the Hamiltonians, but it's all the same. So the Hilbert space is fragmented. And actually this model is equivalent to the XXZ model, by regarding, if we restrict to the action of the Hamiltonians in the subspace consisting of a certain kind of two spaces out of 2s plus 1 spaces of the total entire Hamiltonians, then we can say that this restricted Hamiltonian is integrable Hamiltonians by regarding the one species with upspin and the other one with downspin. So indeed, we can get the integrable Hamiltonian with some parameters which depends on the choice of the species. So in each species, we have different kinds of integrable models in this case. So total Hamiltonian is not integrable, but if we restrict the action of the Hamiltonian in the space, which consists of only 2 degrees of freedom, then we get integrable Hamiltonian. So I'm not sure about this is more understandable or not, but the other example is maybe more understandable, which I called XXC model. So this is actually completely integrable models because there exists our matrix which solves the Yang-Max equations. And this is integrable in the sense that if we remove the degree of freedom between 0 and 2, and then we get this integrable Hamiltonian. So this is a completely integrable Hamiltonian, but still it exhibits some fragmentations. Okay, so this is the local Hamiltonian. And the idea is to find the partial configurations which never changes by the action of the Hamiltonian. So if we have these initial conditions and then apply the Hamiltonian, then we get totally 1, 2, 3, 4, 5, 6 different configurations. But if you look at these 6 configurations carefully, then we always get the partial configuration consisting of 0 and 2 is given by 0, 2, 0, 2. So this partial configuration never changes by applying the Hamiltonian. Only the position of 1 can be different in each configuration. Okay? So by neglecting the position of 1s, we always get 0, 2, 0, 2. So this is the frozen partial configurations of the system. So we call this the irreducible strings, and the Hamiltonian is the Hilbert space is fragmented according to this partial configurations. So, okay, so this is a rough idea of the Hilbert space fragmentations. So we have an XXC model, which is almost like another integral of the Hamiltonians. And in each Hamiltonians, we have some associated frozen partial configurations, which is given by all the zeros with arbitrary number of 1s between them. And we can also have 0, 0, 0, 0, 0, 2, and some 1s at arbitrary positions, and so on. So, but if we neglect all 1s, we always have the same zeros here, the same configuration consisting of 0 and 2. So this is the idea of the Hilbert space fragmentations of the XXC model according to the irreducible strings consisting of 0 and 2. Okay, so we are dealing with the integrable models, but it is of course possible to perturb it by adding some extra terms. And then usually the perturbation violates integrabilities, but it is sometimes possible to keep the Hilbert space fragmentation. So I said that the Hilbert space is fragmented according to the partial configuration consisting of 0 and 2. So the idea is if we add the perturbations which does not exchange 0 and 2, then we still have the Hilbert space fragmentations, but these terms may violate the integrability of the model. So the options are listed here. So if we add these terms, this never exchanges 0 and 2, and this never changes the configuration of 0 and 2. So this violates the integrability of the models, but does not violate Hilbert space fragmentation. And sometimes it is possible to keep the integrability in a selected subspace. For instance, if we properly choose the coefficient of this which is denoted by DSS or DS1 and so on, then we will get the models which is partially solvable only in the subspace consisting of the reducible strings 0s over 2s. So this is possible by choosing this kind of perturbations, because in this reducible string subspace, the sequence of 0, 2 or 2, 0 never shows up. So we always have zeros, only zeros, or only 2s. So 0, 2 never shows up, 2, 0 never shows up. So this perturbation occurs as 0 in this selected subspace. Okay, so in this selected subspace, and this selected subspace, the Hamiltonian in this selected subspace can be mapped to the non-integrable systems. So this is integrable in this subspace, but this usually do access non-zero in generic subspace, so it violates integrability in the entire Hilbert space. So we don't have Yang-Baxter equations in the entire Hilbert space anymore, but if we restrict the axiom Hamiltonian in this subspace, then we again obtain the emergence of Yang-Baxter equation. Okay. So similarly, we can play the same game with this. And then I want to proceed to the conclusions. So I explained that it is possible to embed the integrability into the partially solvable models or Hilbert space fragmented Hamiltonians. And what's interesting? Why is this interesting? Why is it interesting to embed this integrability to the non-integral Hamiltonians? Because in the non-integral Hamiltonians, everything is very difficult because we cannot compute anything. We thought that everything cannot be computed in the non-integrable systems, but it turned out that if there is a partial integrabilities, we can compute the things at least in this solvable subspace. And of course, integrability violates thermalizations. So this partially is a non-integral system with partial solvability may exhibit some different properties from the normal, non-completely non-integral systems. So, okay, so okay, I stop here. So thank you.
Okay, I think idea is very nice. Okay.
Thank you.
About the UV complexities after you embedded into our model, and then still working on you are the complexities, UV complexities, is still working on.
It's okay. So I constructed some examples which admit some partial integrabilities. And I think we almost understand the mechanism, but there should be another mechanism which explains the partial integrability. So this is not the end of the story.
Some evidence, numerical evidence on this kind of complete.
Yes. Okay. This is what we observed.
Okay. And then how about you have the spin-on case? How about the Harden is a spin half chain? So can you work out the same thing on?
Yes, in Harden chain, I think there is no partially solvable subspace.
Right.
So,
That's if there is a change of boundary to the half spin. That's I think the problem. The open barren boundary, you would get some problem.
Yeah, as you can imagine, it is very difficult to find a partially solvable subspace. But if we compute, for instance, if we compute some energy spectrum, then we observe the equal space spectrum. This is a very strong sign there exists a restricted spectrum generating algebra, but we didn't check it yet. And because from the viewpoint of SPT phase, it's saying there should be some connection to this model. So we sometimes we already have some evidence of the emergence of the SPT natures, even for the excitation state.
One more question: instead of observing the magnon, your magnon, how about the Brighton?
Brighton. I spin two. Okay, so okay, I showed only one type of quasi-particle excitation, but in the EGLT model, there are various kinds of quasi-particle excitation which can be exactly solvable. So, okay, I didn't remember whether the Krypton is included in that series, but there should be the other one. For instance, alphas A or alphas B could be different kind of solvable energy eigenstates.
Okay, thank you.
Thank you.
Yeah, ignorant question, but your example of partially solved model comes from lattice model.
Yes.
And then I wonder how to distinguish which state is not thermal.
Yes, that's a very good question, and that's a very difficult task, actually. So, okay, in the first place, it is very difficult to say the model is really non-integrable. So, because there would be some models which is not discovered as integrable systems, but there are some evidence, some numerical evidence, which is given by some energy level statistical, we call it like that. So the integrable models and non-integral model, it shows different distributions. And we can also check it by checking analytical checks by loss-taking conditions. So maybe you can Google it, there are several differences. And for the non-thermal or thermal states, so this is the example. So we can just check this. Okay, so if we see the emergence of the oscillations, this is not the thermal state, of course. And the second one is this entanglement entropy. So if we have some isolated point, this should be counted as the non-thermal state, because this has a very different nature from the normal thermal state. But of course, it is very, very hard to say what is really non-thermal and what is really thermal.
non-integral or partially integral models that are known to be in the class of the KPZ or something like that.
KPZ, yes, KPZ can be observed in the quantum systems. KPZ can be observed in the isotropic XXX model. So I think I put it in the last slide. So this is the emergence of KPZ in the isotropic XXX model. And of course, we can embed the XXX model in our partially integral models. So I strongly expect the emergence of this KPZ universality class in the subspace, this subspace of XXX models. But of course, if we compute the things in the entire Hilbert space, I guess we will observe just Gaussian distributions instead of the KPZ.